Voyager's journey to Andromeda. The devastating truth. Picture this. We live in a moment in human history where we've sent machines, actual robots, beyond the edges of our solar system. These aren't just any machines. They're ambassadors of humanity, sailing through the cosmic ocean with messages from Earth, carrying the golden record, a time capsule from our civilization. But here's where it gets genuinely thought-provoking. Scientists just calculated something that fundamentally changes how we should think about our place in the universe. And honestly, it's devastating in ways you might not expect. Let me start with something that might surprise you. When you hear the word space, your mind probably conjures images of Star Trek, of ships jumping between stars and moments, of civilizations spread across galaxies. But the universe doesn't work like that. The universe is almost incomprehensibly big, and our current understanding of physics suggests that nothing, absolutely nothing, can travel faster than light. This isn't just a limitation of our technology. This is the fundamental law of reality. Now, imagine sending a spacecraft on the longest journey imaginable. Not to the moon, which is just 240,000 miles away. Not even to Mars, which is tens of millions of miles distant. Imagine sending a spacecraft to another galaxy. Not just any galaxy, but the closest one to us, the Andromeda galaxy. And imagine that this spacecraft has been traveling for over 50 years already, moving at speeds that would take you from New York to Los Angeles in about 12 minutes. That's Voyager 1. And Voyager 2, her twin, right behind her. The Voyager missions launched in 1977, almost 50 years ago. Think about that for a moment. When these spacecraft were launched, dinosaurs were extinct for millions of years. Ancient Rome was ancient history. The pyramids had been standing for 4,500 years. And we sent machines into space that are still sending data back to Earth, still operating, still exploring the frontier beyond our solar system. But here's the thing that haunts astronomers and physicists. Here's what keeps them up at night in their offices at NASA, at the Jet Propulsion Laboratory at universities around the world. Scientists have finally, with modern calculations and improved understanding of Voyager's current velocity, computed exactly how long it will take for these spacecraft to reach Andromeda. And the number is so staggeringly, impossibly large that it forces us to confront the true scale of the universe in a way that abstract numbers simply cannot do. 2.5 million years. That's not a typo. That's not a round number chosen for dramatic effect. 2,500,000 years. That's how long Voyager will take to reach the nearest major galaxy. To put that in perspective, 2.5 million years ago, our ancestors, Homo habilis, were just beginning to use stone tools. They were learning how to break rocks in specific ways to create sharp edges. They weren't thinking about art, philosophy, or science. They were thinking about survival. They didn't have language the way we understand it. They didn't have culture in any recognizable form. Fast forward 2.5 million years to today, and we have civilization. We have philosophy, mathematics, astronomy, medicine. We've gone from using sticks to manipulate our environment to splitting atoms and landing robots on Mars. We've built the internet. We've decoded the DNA molecule. We've photographed black holes. We've created artificial intelligence. In just 2.5 million years, the exact same amount of time it will take Voyager to reach Andromeda, we've gone from primitive stone tool users to a spacefaring civilization, at least in our infancy. Now, think about what might happen in the next 2.5 million years. If human civilization, if Earth itself still exists, if we've learned to extend our lifespans, to travel further, to understand more, the technological changes ahead will dwarf the changes we've already experienced. And yet, Voyager will still be traveling, still moving toward a destination it may never reach, at least not while anything resembling human civilization still exists on Earth. This is the devastation that scientists are grappling with. It's not just the numbers. It's what those numbers reveal about the fundamental nature of existence. It's about the isolation of our world. It's about the impossible distances that separate galaxies and the equally impossible timescales that separate events in the cosmic story. Let's talk about Voyager specifically. These weren't designed to be the longest-lasting spacecraft in history. When they were built, the expectation was that they might last 5 years, 10 at the absolute maximum. They were sent to Jupiter and Saturn to study those magnificent worlds and their moons. That was the original mission. 5, maybe 10 years of operation. But something remarkable happened. These machines were built with such incredible precision, with such redundancy and cleverness, that they kept working. They kept transmitting data back to Earth. Long after their mission to Jupiter and Saturn was complete, they were still functioning, still exploring. Voyager 1 became the first spacecraft to reach the heliopause, the boundary of our solar system where the solar wind finally loses its ability to push against the interstellar medium. As of now, as I'm speaking to you, Voyager 1 is roughly 14.5 billion miles from Earth. That's almost 100 times the distance from Earth to the Sun. It's traveling at about 38,000 miles per hour relative to the Sun. It's moving away from us at roughly 3.6 astronomical units per year. An astronomical unit is the distance from Earth to the Sun, about 93 million miles. So every single year, Voyager 1 travels a distance equivalent to almost 4 times Earth's distance from the Sun. That's fast. Incredibly fast compared to any human standard. But Andromeda is 2.5 million light-years away. A light-year is the distance that light, the fastest thing in the universe, travels in 1 year. Light moves at about 186,000 miles per second. In 1 second, light travels almost 8 times around the Earth's equator. In 1 year, light covers a distance of about 5.88 trillion miles. And Andromeda is 2.5 million of those light-years away. Now let's do the math. Voyager's current velocity is 38,000 miles per hour. To reach Andromeda, it needs to travel 2.5 million light-years, which is about 14.6 sextillion miles. That's a number with 21 zeros. A sextillion. It's a number so large that it becomes almost meaningless to humans. When you divide that distance by Voyager's speed, you get approximately 2.5 million years. 2.5 million. Some calculations vary depending on whether you account for the solar system's motion relative to the galactic center, whether you include acceleration and deceleration, whether you factor in stellar drift and gravitational influences. But they all come to roughly the same conclusion. The journey will take millions of years. And here's where it gets genuinely unsettling. Voyager 1 isn't accelerating. It's not running toward Andromeda like a rocket chasing a star. It's coasting. It's drifting. Solar wind once pushed on it, but that pushed it almost equally in all directions. Now, as it moves further away from the Sun, it's effectively just floating through space, sustained by its initial momentum, gradually slowing as it encounters the sparse particles of the interstellar medium. In fact, Voyager 1 is slowing down. Very slowly, but slowing. Eventually, millions of years from now, it will be moving so slowly relative to the galaxy that any planets or asteroids in the Andromeda galaxy could effectively capture it. But that's assuming nothing hits it. That's assuming no rogue asteroids, no stray comets, no cosmic debris intercepts its path over those millions of years of travel. The probability is low, but across millions of years, probability becomes reality. Let me paint you a picture of what space actually looks like, because I think most people have a false impression. When we look at diagrams of the solar system, or when we see Hubble Space Telescope images of distant galaxies, there's something about the way they're rendered that's misleading. The images are often colorized. Stars and galaxies are often overlaid on black backgrounds. And we get this impression that space is full of stuff, that it's crowded. The reality is the opposite. Space is almost incomprehensibly empty. The distance between stars in our galaxy is measured in light-years. Light-years. 1 light-year is the distance light travels in an entire year, 5.88 trillion miles. And most stars are at least a few light-years apart. Some are tens of light-years apart. In the densest regions of the galaxy, stars might be only a light-year or 2 apart. In the sparse regions, they might be 20 or 30 light-years apart. Now think about what that means for Voyager. In 2.5 million years of travel, Voyager will encounter how many stars? If stars are separated by several light-years on average, and Voyager is traveling at 38,000 miles per hour, and it will be traveling for 2.5 million years, the answer is likely 0. It will probably never come within a light-year of any star. It will drift through the spaces between galaxies. A lonely machine, carrying Earth's music and mathematics, alone in the dark. This is the devastation. It's the profound isolation revealed by these numbers. But let's back up. Let's understand how we even know Voyager's trajectory and speed with enough precision to make these calculations. Voyager is incredibly far away. It's beyond the orbit of Pluto. It's beyond the heliopause, the boundary of the solar system. And yet, NASA's Deep Space Network, a collection of massive radio antennas positioned around Earth, can still receive signals from it. Those signals are weak, incredibly weak. The power output of Voyager's transmitter is about 20 watts, the same power as an old incandescent light bulb. And it's sending signals across a distance that's increasing by roughly 540 million miles every year. The power density of those signals when they reach Earth is infinitesimal. But the antennas of the Deep Space Network are so sensitive that they can still detect and decode them. This is one of humanity's greatest engineering achievements, not just building Voyager, but maintaining communication with it across these impossible distances for over 50 years. The data we receive from Voyager includes precise information about its velocity, derived from the Doppler shift of its radio signal. When something moves away from you, the wavelength of its light or radio waves stretches, shifting to lower frequencies. It's the same effect you hear when an ambulance passes you. The siren sounds higher-pitched as it approaches and lower-pitched as it moves away. By measuring exactly how much Voyager's radio signal is shifted, scientists can calculate its velocity with remarkable precision. They know exactly how fast it's moving, and they can use this to calculate its trajectory through space. But here's something fascinating. Voyager's velocity hasn't remained constant. When it was launched in 1977, it was moving at approximately 36,000 miles per hour. But then it performed flybys of Jupiter and Saturn, using those planets' gravity to accelerate further. This is called a gravity assist. It's a maneuver where a spacecraft approaches a massive planet, and the gravity well of that planet accelerates the spacecraft without any fuel expenditure. Voyager 1 encountered Jupiter and was accelerated further. Then it was accelerated by Saturn. By the time it left the outer solar system, it was moving at approximately 38,700 miles per hour relative to the Sun. Voyager 2 took a slightly different trajectory, traveling to Uranus and Neptune as well, resulting in a slightly slower final velocity of about 35,000 miles per hour. So both spacecraft are being pulled back very slightly by the Sun's gravity. As they move further away, the Sun's gravitational pull weakens, but it's always there, always pulling backward. This means that, over the course of millions of years, Voyager will gradually decelerate. Its speed relative to the Sun will decrease. Astronomers have accounted for this in their calculations. They've calculated Voyager's trajectory not just based on its current speed, but based on how its speed will change as it moves further from the Sun, as it drifts through the sparse matter of the interstellar medium, as it eventually enters the gravitational field of the Andromeda galaxy and begins to be pulled toward it. The numbers still come out to roughly 2.5 million years. Now, you might ask, why does this matter? Why should we care how long it takes a robot we launched 50 years ago to reach another galaxy? We're not going to live that long. Humanity might not live that long. Why is this calculation even important? Here's why. Because Voyager represents something profound about human ambition and human understanding. The golden record aboard Voyager contains music from Earth. There's Bach, there's Beethoven, there's Mozart, there's Chuck Berry. There's a recording of greetings in dozens of languages. There's sounds from Earth, wind, rain, thunder, whales singing. There are photographs of Earth and human civilization. There are scientific data and mathematical definitions. This was Carl Sagan's vision. He believed that we should send something into the cosmos that represented humanity at our best, that expressed our capacity for beauty, for mathematics, for understanding the universe. He thought that maybe, just maybe, in the distant future, some other civilization might find Voyager and learn about us. The reality is that Voyager will probably never reach any civilization. It will drift through empty space for millions of years. The Sun will eventually become unstable, will expand, will die. In about 5 billion years, the Sun will become a red giant and engulf the inner planets. Earth will be destroyed. Humanity, or whatever we might evolve into, will either have spread to other worlds or will have ceased to exist. And Voyager will still be traveling. Think about that. Long after Earth is destroyed, long after the sun dies, long after the galaxy itself changes shape and form due to gravitational interactions with other galaxies, Voyager will still be out there. Still carrying that golden record. Still moving infinitesimally slowly toward Andromeda. This is both profound and devastating. It's the ultimate message in a bottle. We've cast it into an ocean with no shores, no destinations, where it will drift forever, or at least until it's captured by some other gravitational force. Let me tell you something else that's devastating about this calculation. Andromeda isn't just the nearest major galaxy. There are other galaxies closer to us. The Large Magellanic Cloud is about 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years away. These are dwarf galaxies, much smaller than either the Milky Way or Andromeda, but they're closer. Voyager won't reach them first. At its current trajectory, Voyager isn't heading toward either of the Magellanic Clouds. It's heading in a different direction. It's heading toward Andromeda because that's where we pointed it, because Andromeda is the second largest galaxy in the local group after our own Milky Way, because it's magnificent and visible to the naked eye from Earth on clear nights, and because it's a destination that humans can imagine, can dream about, can work toward understanding. But to actually reach it, Voyager has to travel through the void, through empty space, for a duration so long that it's difficult to comprehend. Now, let me contextualize this in another way. Imagine that you're standing on a beach, looking out at the ocean. The horizon seems distant, but you know intellectually that it's not that far away. Maybe a few miles, a few kilometers, infinitesimal compared to the size of Earth. Now imagine that instead of a few miles to the horizon, there were 2.5 million miles of empty water, and at the end of that water, there was nothing but more water for another 2.5 million miles. Imagine trying to cross that ocean with a boat that moves at 38,000 miles per hour, which sounds fast, but which would still take millions of years to complete the journey. That's what Voyager is attempting to do in the cosmic ocean. Actually, let me correct that analogy. It's worse than that. At least in my ocean analogy, the water is there. Voyager isn't traveling through water or air or any medium we're familiar with. It's traveling through space, through a vacuum, through the void. There's almost nothing there. Interstellar space has a density of perhaps 1 atom per cubic centimeter. One single atom scattered throughout a volume the size of your sugar cube. Imagine trying to sail a boat through something so sparse that there's essentially nothing to push against. That's what Voyager is doing. It's coasting on its initial momentum, gradually being pulled back by the sun's gravity, heading toward a destination that's so far away that the numbers lose meaning. Let's talk about what Voyager's designers were thinking when they created this spacecraft. Voyager wasn't designed as a one-way mission to another galaxy. That would be absurd. The technology was created in the 1970s. The spacecraft was supposed to explore Jupiter and Saturn, study their moons, conduct scientific experiments, and then, presumably, either be abandoned or directed into the sun to burn up. But because the spacecraft was so well engineered, because redundancy was built into every system, because the engineers thought carefully about how to make it robust and reliable, Voyager kept working. It exceeded its expectations by a factor of millions. It's still working today, nearly 50 years after launch, still sending data back to Earth, still exploring the frontier of human knowledge. This is remarkable. Most spacecraft designed in the 1970s would be defunct by now. They'd be broken down by radiation, degraded by the cold of space, lost to mechanical failure. But Voyager keeps going. It's the Energizer Bunny of space exploration. It just keeps going and going and going. And because it keeps going, it will eventually reach Andromeda, even if it takes 2.5 million years. Let me tell you about the Andromeda galaxy itself, because to understand the devastation of Voyager's journey, you need to understand what Voyager is traveling toward. Andromeda is visible to the naked eye. On a clear night, away from city lights, you can look at the sky and see a fuzzy patch of light. That's Andromeda. It's the most distant object visible to the human eye without optical aid. That faint smudge of light you're seeing is actually composed of roughly 1 trillion stars. 1 trillion. That's a million. If every person on Earth, all 8 billion of us, counted stars without sleeping for their entire lives, we still wouldn't count to 1 trillion. Andromeda is larger than our own Milky Way. It's more massive. It has more stars. If you could somehow zoom out far enough to see both Andromeda and the Milky Way from a distance, Andromeda would dominate the view. It would be the larger of the two. And yet, it's only 2.5 million light-years away. It's our nearest galactic neighbor. Imagine if the nearest city to yours, instead of being a few hours' drive away, was 2.5 million times the age of human civilization away. That's the scale we're talking about. Andromeda contains stars of all types. There are red giants, slowly dying stars that have expanded into enormous orbs. There are white dwarfs, the dense cores of dead stars, so compressed that a teaspoon of white dwarf material would weigh as much as an elephant. There are blue supergiants, massive stars burning through their fuel at incredible rates. There are stars like our Sun, medium-sized and stable. There are small red dwarfs, the most common type of star in the universe, burning slowly and quietly for trillions of years. Around these stars, there are probably planets. Billions of them, potentially. Some might be rocky like Earth. Some might be gas giants like Jupiter. Some might be ice worlds. Some might have water. Some might have atmospheres. Some might have life. That's what makes the Andromeda galaxy so fascinating to scientists. It's not just a distant collection of stars. It's a potential harbor for billions of worlds, potentially billions of civilizations, potentially billions of stories and histories and futures. And Voyager is heading toward it as our ambassador, as our message in a bottle cast into the cosmic sea. When Voyager finally reaches the Andromeda galaxy, if it reaches it, if nothing intercepts it, if the galaxy hasn't already collided with the Milky Way by that time, what will it find? What will the universe look like after 2.5 million years? The answer is we don't know. We can't know. We can make educated guesses, but they're just guesses. Here's what we do know will definitely happen. The Milky Way and Andromeda are approaching each other. We can measure this. We can observe that Andromeda is moving toward us at a velocity of about 300 kilometers per second. It's approaching, and in about 4.5 billion years, the two galaxies will collide. Now, collide might not mean what you think it means. The galaxies are so large and stars are so sparse that actual collisions between individual stars are unlikely. But the two galaxies will merge. They'll interact gravitationally. Stars will be flung out into space. Clouds of gas will compress and heat up. Star formation will increase. Black holes, the supermassive black holes at the centers of each galaxy, will eventually merge into an even larger black hole. The result will be a new galaxy. Not the Milky Way, not Andromeda, but a merger of the two. Astronomers often call this Milkdromeda or Andromedki, or some other mashed-up name. It's a poetic way of acknowledging that in the distant future, these two distinct galaxies will become one. This means that when Voyager reaches Andromeda, or rather, when Voyager reaches the coordinates in space where Andromeda currently is, and would have been for millions of years, Andromeda might not exist anymore as a separate entity. It might already be merged with the Milky Way. The universe might look completely different. Actually, let me clarify the timeline. Voyager will take 2.5 million years to reach Andromeda's current position. The Milky Way and Andromeda will collide and merge in about 4.5 billion years. So Voyager will have already reached Andromeda's current location billions of years before the actual collision happens. This is because space is expanding. The universe is getting bigger. The distance between us and Andromeda is increasing over time due to the expansion of space itself, a phenomenon that's been accelerating due to something we call dark energy. Wait, that's not quite right. Let me correct myself. Andromeda is moving toward us due to its own motion through space. The expansion of the universe is happening, but it's not strong enough yet to overcome the gravitational attraction between our galaxy and Andromeda. So Andromeda is falling toward us in a sense. It's being attracted to us. But the expansion of space is counteracting this, slowing the approach. The net result is that Andromeda is approaching us, but slowly. In 4.5 billion years, the two galaxies will collide. The collision will take billions of years to complete. Stars will orbit chaotically. The orderly spiral structure of both galaxies will be disrupted. Gravity will reshape everything. But Voyager, drifting through space, will barely notice. A spacecraft traveling at 38,000 miles per hour through a galaxy containing 1 trillion stars is incomprehensibly insignificant. Voyager would have to be incredibly lucky to encounter anything at all. Let me talk about luck for a moment because this is important. In 2.5 million years of travel, what's the probability that Voyager will encounter something? A star? Planet? An asteroid? An alien civilization? The answer, mathematically, is very low. Space is so vast and so empty that random encounters are almost impossible. If you launched 100 billion spacecraft in random directions, traveling for 2.5 million years each, most of them would pass through the entire volume of the Andromeda galaxy without coming within 1 billion miles of any star. But Voyager isn't traveling in a random direction. Humans chose its trajectory. We pointed it at a destination and launched it. Does that increase the probability of encountering something? Slightly, but not significantly. We didn't point Voyager directly at Andromeda's center, at the supermassive black hole lurking there, at a star cluster, or at any particular feature. We simply launched it on a trajectory that would eventually take it to that region of space, assuming nothing interfered. What could interfere? What could deflect Voyager from its path? The gravity of stars. If Voyager passed close to a star, that star's gravity would pull Voyager off course. The intensity of this deflection would depend on how close Voyager comes to the star and how massive the star is. A close approach to a large star could significantly alter Voyager's trajectory. A distant approach to a small star might barely change it. There's also cosmic dust and gas. As Voyager travels through interstellar space, it encounters particles. These particles are so sparse that they don't significantly slow Voyager, but they do exist. Over millions of years, Voyager's trajectory might be altered slightly by the cumulative effect of countless tiny gravitational interactions with these particles. And then there's the gravitational field of the Milky Way itself. Voyager is still within the gravitational influence of the Milky Way. The galaxy is massive, millions of times more massive than the Sun. Its gravity extends far beyond the visible disk of stars. Voyager is currently in the galactic halo, the region of sparse matter that surrounds the galactic disk. As Voyager travels, it will gradually escape the Milky Way's gravity. Eventually, it will reach the heliopause of the local group, the gravitationally bound region containing the Milky Way, Andromeda, and about 100 other smaller galaxies. At that point, it will be traveling through intergalactic space, in the void between galaxies. This void is even more empty than interstellar space. There's almost no matter. The density is perhaps 1 atom per 1,000 cubic centimeters or worse. It's nearly a perfect vacuum. All of this is to say that Voyager's path is uncertain. We can calculate where it's currently heading, and we can extrapolate forward to estimate its path. But over 2.5 million years, countless gravitational interactions and chance encounters could alter its trajectory significantly. Despite all of this, Voyager will eventually reach the region of space where Andromeda is or was or will be. And when it does, it will be carrying that golden record. It will be carrying humanity's message to the cosmos. What message are we sending exactly? What did we choose to put on the golden record? Carl Sagan and a committee of scientists, artists, and thinkers assembled a collection of sounds and images that they believed represented humanity at its best. They chose music from the classical tradition: Bach, Beethoven, Mozart. They chose folk music from around the world. They chose nature sounds: wind, rain, thunder, birds singing, whales singing. They chose greetings in multiple languages. They chose images, images of human civilization, images of art and culture, images of our world. They included scientific data, mathematical definitions, chemical formulas, a message to any civilization that might find the spacecraft. The record was designed to survive for billions of years. It's made of copper with gold plating. The grooves are etched into the metal. There's a stylus included with the spacecraft, the idea being that any civilization advanced enough to find Voyager would presumably be advanced enough to figure out that a stylus and grooves mean there's information encoded there. The record contains 116 images and about 90 minutes of music and greetings. When you think about it, it's an act of profound optimism. We're assuming that 1. Voyager will be found. The probability of this is extraordinarily low, as we've discussed. 2. The civilization that finds it will be able to decode it. They'll understand that the grooves contain information. They'll have the technology to read it. They'll understand that the images and sounds represent something important. 3. They'll understand that we're trying to communicate with them. They'll recognize the music as music, not random noise. They'll recognize that the greetings are voices, not mechanical sounds. They'll understand the intent. This is a profound act of faith in the universality of human culture and experience. We're assuming that civilizations on opposite sides of the cosmos might somehow find meaning in our music, our images, our voices. Maybe they will. Maybe the mathematical formulas and chemical definitions are universal. Mathematics and chemistry are the same throughout the cosmos. 2 + 2 = 4 everywhere. Hydrogen is hydrogen everywhere. The periodic table of elements is the same on distant worlds. But music, art, culture, these are human expressions of something deeper. Emotions, the joy of creation, the need to express ourselves, the yearning to communicate. If an alien civilization finds Voyager, and if they can decode the golden record, they'll hear Chuck Berry singing Johnny B. Good, a rock and roll song from 1958. What would they make of that? How would they interpret electric guitars? How would they understand the cultural significance of a song about a boy who wanted to be a rock and roll star? It's a mystery, but that's the point. We're sending the record knowing that we don't fully understand how it will be received, if it's received at all. And Voyager will carry that record for 2.5 million years, traveling through the void, eventually reaching the region of space where Andromeda exists. Now, let's talk about what will actually happen when Voyager reaches Andromeda's region. Because reaching Andromeda doesn't mean reaching the center of the galaxy or finding some obvious destination. It means traveling 2.5 million light-years in the direction we sent Voyager. The Andromeda galaxy is enormous. It has a diameter of about 200,000 light-years. But most of that is the halo, the sparse outer region. The disk, where most of the stars are, is about 100,000 light-years in diameter. And the density of stars increases toward the center. Voyager will be heading toward a region in space. Whether it hits a star, a planet, or empty space depends on its exact trajectory and the exact locations of objects in Andromeda. Actually, hits is the wrong word. Space is so vast that the probability of Voyager actually impacting something is vanishingly small. But it will enter Andromeda's region. It will pass through the galaxy. And as it does, it will be gradually pulled more strongly by Andromeda's gravity. The galaxy's gravity well will slow Voyager down. Eventually, if Voyager passes close enough to Andromeda, it could be captured by the galaxy's gravity. Could become part of Andromeda. It could orbit the supermassive black hole at the center, spiraling inward over billions of years, until eventually it's destroyed. But this is speculation. We don't know Voyager's exact trajectory. We don't know if it will pass through the heart of the galaxy or around its edges. We don't know what gravitational perturbations will occur over millions of years. What we do know is that Voyager will take approximately 2.5 million years to reach the coordinates where Andromeda currently is located. And that's the devastating fact. That's what scientists calculated. That's what's been keeping astronomers awake at night, because it forces us to confront the true scale of the universe. Let me give you some perspective on this 2.5 million year duration. 2.5 million years ago, hominins in Africa were walking on 2 legs. They had opposable thumbs and were beginning to understand that they could use objects as tools. They were not yet human. They did not have language. They had no understanding of astronomy, of physics, of mathematics, of art beyond the most basic expressions. They did not know that 2.5 million years in the future, their descendants would build machines and launch them into space. They could not have imagined it. They could not have conceived of it. Now, imagine that it's 2.5 million years in the future. What will humans, or whatever we've evolved into, be capable of? What will our understanding of physics be? What will our technology be? If history is any guide, the changes will be unimaginable. We've gone from stone tools to splitting atoms in about 10,000 years of civilization, less than 0.4% of the 2.5 million-year journey Voyager will take. Imagine what 2.5 million years of progress might bring. Perhaps humans will have uploaded their consciousness to computers. Perhaps we'll have developed faster-than-light travel, overcoming the fundamental barrier that Einstein's relativity seems to forbid. Perhaps we'll have engineered our biology to extend our lifespans to millions of years. Perhaps we'll have spread throughout the galaxy, established colonies on planets around other stars. Or perhaps Earth will be destroyed. Perhaps humanity will have destroyed itself. Perhaps we'll have been wiped out by asteroid impact or disease or war. The point is, we don't know, and Voyager will be traveling regardless. This is the devastating aspect of this calculation. It's not just that Voyager will take an impossibly long time to reach its destination. It's that we'll probably never know whether it arrives. We'll never know if it reaches Andromeda. We'll never know if it's found. We'll never know if our message is received. Let me talk about the future of the Voyager program because it's connected to this larger story. As we speak, NASA's Deep Space Network is still receiving signals from Voyager. They're still downloading data. They're still monitoring its status. But this won't continue forever. Voyager's power source is a radioisotope thermoelectric generator. It's powered by the decay of plutonium-238. As the plutonium decays, it releases heat, and that heat is converted to electricity. It's an elegant system. It requires no fuel in the traditional sense. As long as the plutonium is decaying, and plutonium-238 has a half-life of 88 years, the spacecraft has power. But the power output decreases over time. When Voyager was launched in 1977, it had plenty of power. Over the decades, as the plutonium has been consumed, the available power has decreased. Engineers have had to turn off certain instruments, shut down non-essential systems, and carefully manage the remaining power. Current projections suggest that by 2025 or 2026, right around now, Voyager will lose the ability to maintain all of its systems. Within a few years after that, likely by 2030 or 2040, Voyager will lose the ability to power its transmitter. At that point, it will go silent. It will stop sending data back to Earth. Voyager will continue traveling. It will continue its journey toward Andromeda. But humanity will lose contact with it. We won't be able to track its position anymore. We won't know where it is or what it's doing. It will disappear into the cosmos, continuing on its trajectory forever, but forever beyond our ability to observe or communicate with it. This is significant. It means that the longest-running conversation between Earth and a spacecraft will eventually end. The last signal from Voyager will be received. Humanity will have to say goodbye to our most distant ambassador. And then Voyager will be alone, truly alone. For 2.5 million years, it will travel without any contact with Earth, without any purpose except to continue moving forward. This is perhaps the most devastating aspect of all. It's not just the numbers. It's not just the impossible distances. It's the loneliness. Voyager will be a solitary machine, broadcasting its presence to a universe that won't receive it, carrying a message to a cosmos that may never hear it. We designed Voyager to explore the solar system. It exceeded that mission by orders of magnitude. It explored the far reaches of the sun's gravity well. It became our furthest ambassador. But eventually, its mission will end. The power will run out. The transmitter will go silent. And still, it will travel. For millions of years, carrying humanity's greetings, humanity's music, humanity's attempt to say, we were here, we mattered, our voices and our art had meaning. Into an indifferent universe, Voyager will deliver this message. Whether anyone receives it is beyond our control. Whether it changes anything, whether it matters in any cosmic sense, is unknowable. This is the science that astronomers and physicists are grappling with. This is what they've calculated. 2.5 million years for a spacecraft to reach the next galaxy. Let me put this in one more context. Let's imagine that we wanted to send a spacecraft to Andromeda that could arrive in a reasonable time frame, say 50,000 years instead of 2.5 million years. How fast would it need to go? Currently, Voyager travels at 38,000 miles per hour. To reach Andromeda in 50,000 years, a spacecraft would need to travel at roughly 1.9 million miles per hour. That's about 50 times faster than Voyager. With our current technology, we can't achieve those speeds. Not even close. Our rockets can achieve velocities of tens of thousands of miles per hour. But 1.9 million miles per hour is beyond our reach with chemical rockets. Some scientists have proposed ideas that might eventually achieve such speeds. Ion drives can accelerate for much longer than chemical rockets, gradually building up velocity. Solar sails could be pushed by laser beams or radiation pressure from the sun antimatter engines. If we could harness them, could potentially achieve near-relativistic speeds close to light speed. But none of these are currently available. With our current technology, 2.5 million years is a realistic estimate for how long it would take a spacecraft like Voyager to reach Andromeda. And even if we could build a faster spacecraft, even if we could achieve 0.1% light speed or 0.01% light speed, the journey would still take thousands of years, not millions. Still an impossible duration in any practical sense. This is the reality of the cosmos. Distances are vast. Time scales are immense. And the speed limit of the universe, the speed of light, is still too slow to overcome these distances in any reasonable time frame. This is what's devastating about Voyager's calculated journey. It's not that we've discovered something surprising or unexpected. It's that we've quantified something we already knew, that the universe is incomprehensibly vast, and our ability to traverse it is inadequate. We can send machines, but they'll take millions of years to arrive anywhere. We can't travel fast enough. We can't overcome the scale of space. Let me address another aspect of this that I think is worth contemplating. When we say that Andromeda is 2.5 million light-years away, what we mean is that the light we observe from Andromeda today, the light that allows us to see the galaxy in our telescopes, is light that started its journey 2.5 million years ago. When you look at Andromeda, you're not seeing it as it is right now. You're seeing it as it was 2.5 million years ago. A lot could have changed. Stars could have exploded in supernovae. The galaxy could have been altered by interactions with other galaxies. The supermassive black hole at the center could have behaved differently. But we don't know. We can't know. We're limited by the speed of light. Light is the fastest thing in the universe. Nothing can travel faster than light. So if we want to know what Andromeda looks like right now, we'd have to travel there and look. And that journey takes 2.5 million years at Voyager speed. This is a fundamental aspect of relativistic physics. The structure of the universe is such that we can never observe the universe in real time. We can only observe the past. The further away we look, the further into the past we're seeing. When Voyager finally reaches Andromeda in 2.5 million years, what it will see has already been observed by any civilization on Earth at that time, assuming they have telescopes. They'll be observing a galaxy that looks the way Voyager will observe it, thousands of years after Voyager reaches it. Actually, that's not quite right. Let me correct myself. Voyager will reach the region of space where Andromeda is located. It will be traveling at 38,000 miles per hour through space where Andromeda exists. During its journey, as Voyager travels closer to Andromeda, it will begin to observe Andromeda directly. But these observations will still be limited by light's travel time. If Voyager encounters a star in Andromeda, the light from that star will take some time to reach Voyager. If Voyager somehow encounters alien technology in Andromeda, it would take time for communications to travel between Voyager and that technology. All of this is to say that even after Voyager reaches Andromeda, even if it's found and examined by an advanced civilization, the interactions will be limited by the speed of light. There's no way around Einstein's speed limit. This is the reality of the universe. It's a reality that's both beautiful and devastating. It's beautiful because it means that the universe has structure and order. There are fundamental laws that govern how things work. These laws are elegant and mathematical. They're universal. It's devastating because those same laws prevent us from crossing cosmic distances quickly. They condemn any spaceship to a journey of millions of years if it wants to visit another galaxy. They isolate us. They separate galaxies from each other with barriers of time and space that cannot be overcome. Now, you might wonder if the scientists who calculated this journey time are depressed by these findings. Are they devastated? In some sense, yes. Many of them find it profound and moving that we've built a spacecraft that will travel for millions of years carrying our message, knowing that we probably won't live to see it arrive. There's something poignant about that. Something that touches on existential themes, our mortality, our smallness, our place in the cosmos. But there's also something inspiring about it. We built Voyager not because we expected it to reach Andromeda in our lifetime. We built it because we wanted to explore. We wanted to push the boundaries of human knowledge. We wanted to send a message into the cosmos as an act of faith and hope. And it worked. Voyager is still operating, still sending data, still exploring. It's exceeded all expectations. It's become the furthest human artifact from Earth. It's become a symbol of human achievement and human ambition. In a way, the 2.5 million year calculation is also inspiring. It shows that we're beginning to understand our place in the cosmos well enough to make these calculations. We're starting to grasp the true scale of space and time. We're starting to come to terms with how vast the universe really is. This is the next step in human evolution, intellectual evolution, if not biological evolution. We're learning to think on cosmic scales. We're learning to accept that our world is small, our lifespans are brief, and our place in the universe is peripheral. But we're also learning that we can reach beyond ourselves. We can send machines where our bodies cannot go. We can leave messages that will outlast civilization. We can touch the stars, even if it takes millions of years. Let me talk about where Voyager will go after it reaches Andromeda's region. Because reaching the coordinates where Andromeda currently is doesn't mean the journey ends. Voyager will continue traveling. If Voyager isn't captured by Andromeda's gravity, if it doesn't impact a planet or star, it will pass through Andromeda and continue beyond it. The local group of galaxies contains about 100 members. The largest are the Milky Way and Andromeda. But there are other smaller galaxies, Triangulum Galaxy, the Large and Small Magellanic Clouds, and dozens of dwarf galaxies. Depending on its trajectory, Voyager might pass near some of these other galaxies as it continues its journey through intergalactic space. But at some point, it will leave the local group entirely. It will travel beyond the gravitationally bound region of nearby galaxies. At that point, it will be traveling through a universe where the nearest galaxies are millions of light years away. The expansion of the universe will also come into play. Space itself is expanding. The universe is getting bigger. This means that as Voyager travels, the distance to distant galaxies will increase, not just because Voyager is traveling toward them, but because the space between them and Voyager is expanding. Over the course of trillions of years, the expansion of the universe will accelerate. Dark energy, the mysterious force that seems to be accelerating cosmic expansion, will eventually make it so that even light from distant galaxies can't reach Earth. The universe will become dark and cold and empty, but Voyager will still be traveling, still carrying that golden record, still broadcasting its presence to a cosmos that has become incomprehensibly vast and empty. The universe is old. The Big Bang was roughly 13.8 billion years ago. But the universe will exist for trillions of years before it reaches a state of maximum entropy and dies a heat death. Voyager might exist for a significant fraction of the universe's total lifespan, traveling through space long after civilizations have risen and fallen, long after stars have burned out, long after galaxies have collided and merged. This is the scope of the journey we've set Voyager on. It's a journey that extends into the deep future. A journey whose ultimate destination may never be reached. A journey that will probably outlast all of human civilization. And this is the calculating that scientists have been doing. They've calculated that Voyager will take 2.5 million years just to reach Andromeda. They've calculated the velocity, the distance, the probable trajectory. They've accounted for gravitational interactions and the expansion of space. And the numbers come out to roughly 2.5 million years. But I think what's truly devastating about this isn't the numbers themselves. It's what the numbers represent. They represent the isolation of our world. They represent the vastness of the cosmos. They represent the limitation of our speed, our technology, our biology. Voyager will outlast humanity. It will outlast Earth. It will outlast the sun. It will continue traveling when the universe has become so vast and so empty that light from stars will be millions of light years apart. It will continue traveling through a cosmos that has cooled to near absolute zero. We don't know what will ultimately happen to Voyager. Will it be captured by a galaxy and gradually sink into the supermassive black hole at the galaxy center? Will it be hit by an asteroid? Will it be discovered by an advanced civilization and studied? Will it simply drift forever through space, never encountering anything, carrying its golden record as an eternal message to no one? The truth is that we can't know. We can calculate its trajectory. We can estimate how long it will take to reach Andromeda. But we can't predict what will actually happen to it over the course of millions of years. There are too many variables, too much uncertainty, too much time for unexpected things to occur. This is perhaps the most devastation of all. It's the realization that even though we can send a spacecraft, even though we can put it on a trajectory toward another galaxy, even though we can calculate how long it will take to get there, we ultimately can't control what happens to it. We can't protect it. We can't follow it. We can only send it, and hope, and imagine. And that's exactly what we did when we launched Voyager 50 years ago. We sent it with hopes that it would explore, that it would transmit knowledge back to Earth, that it would carry our message into the cosmos. It's done all of those things. It's exceeded our expectations. Now, as it approaches the end of its powered mission, as the plutonium-238 runs out and the transmitter goes silent, we're forced to accept that Voyager's journey is beyond our control. It's beyond our ability to observe or influence. We've sent our ambassador into the cosmos, and we have to let it go. Let me tell you something else about Voyager that adds to the poignancy of this story. Before Voyager went silent, before it left Earth, scientists had to decide what to put on the golden record. They had to decide what messages humans would send into space. What would represent us? What would we want an alien civilization to know about us? Carl Sagan led this effort. He assembled scientists, artists, philosophers, and thinkers. They debated, they discussed, they compromised, and they decided on a collection of sounds and images that they believed captured the essence of human civilization. There's music: Bach, Beethoven, Mozart, Stravinsky, Louis Armstrong, Duke Ellington, Chuck Berry, a Bulgarian folk song, Indian flute music, Peruvian panpipes, Georgian chanting, Aboriginal music, a Japanese mouth organ, a Kenyan song, a wedding song from Azerbaijan. There are sounds of earth, wind, rain, thunder, footsteps, footsteps on pavement, a heartbeat, laughter, a baby crying, a dog barking. There are greetings in 55 languages. In English, there's a simple greeting from the Secretary General of the United Nations. As the Secretary General of the United Nations, an organization of the people of the world, I send greetings on behalf of the people of Earth. We step out of our solar system, uncertain of what we will encounter and desirous of peaceful contact with any people elsewhere in the universe. We are attempting to survive our time so we may live into yours. In Russian, a cosmonaut says, "I am glad to greet you all." In Hebrew, a person says, "Greetings to all inhabitants of the universe." In Swahili, "We are hoping this will reach you in good health and in a spirit of peace." In Arabic, "This is a message from a small and distant world." In Mandarin, "Friends of space, how are you all?" And in 50 other languages, humans say hello to beings we don't know if we'll ever meet, on worlds we've never seen, in a universe we barely understand. This is what Voyager carries. Not just scientific data, not just mathematical definitions, but greetings. Humanity's attempt to say, "We're here, we're thinking of you, we hope you receive this message." It's beautiful, it's hopeful, it's the best of what humanity can be. And now we know that Voyager will take 2.5 million years to deliver those greetings to Andromeda. 2.5 million years. That's the devastating fact. Let's think about what this means for the future of space exploration. If it takes 2.5 million years for a spacecraft like Voyager to reach the next galaxy, how will humans ever explore beyond our galaxy? The answer is we won't. At least not with our current technology. We won't send generation ships that take millions of years. We won't populate Andromeda with human colonies. The universe is too vast. The distances are too great. The time required is too long. This doesn't mean we'll never leave our galaxy. It means we'll have to develop technology that's fundamentally different from what we have today. We'll have to overcome the speed of light barrier. Or we'll have to develop ways to extend human lifespans to millions of years so that individuals can survive the journey. Or we'll have to upload human consciousness into machines that can survive indefinite periods. These are science fiction concepts today. But in 2.5 million years, they might be as commonplace as smartphones are to us today. The point is that the universe is changing our understanding of what's possible. The distances are so vast that they force us to think differently. They force us to imagine new technologies, new solutions, new ways of approaching problems. This is the beauty hidden within the devastation. Voyager's 2.5 million-year journey is impossible by today's standards. But it's a reminder that the universe will demand new solutions from us. It will demand that we push the boundaries of technology and knowledge. And who knows what we'll achieve in the next few thousand years, let alone millions of years. Let me also talk about what Voyager's calculations reveal about the nature of time itself. 2.5 million years is a duration that exists in human consciousness only as an abstraction. We can't visualize it. We can't really imagine it. But in the context of the universe, 2.5 million years is an incredibly short period. The universe is 13.8 billion years old. 2.5 million years is about 0.02% of the universe's current age. It's a blink of an eye, and yet 2.5 million years is longer than human civilization has existed. It's longer than recorded history. It's longer than any human artifact has survived. Voyager will be the first human artifact to travel for a significant fraction of the universe's total age. It will outlast civilizations. It will outlast species. It will outlast continents and mountain ranges and weather patterns. This reveals something profound about time. It shows that human time and cosmic time exist on completely different scales. We experience time as days, weeks, years, decades. We can barely conceive of a century. A millennium seems impossibly distant. A million years is beyond our ability to comprehend. But the universe experiences time on scales that trivialize human duration. A million years is a nothing. A billion years is the lifespan of a star. The universe itself is billions of years old. Voyager will carry humanity's message across scales of time that are almost incomprehensible to us. And when it arrives at Andromeda, if it arrives, it will have been traveling for a duration so long that any civilization it encounters will have arisen and possibly fallen many times over. This is the perspective that Voyager's journey gives us. It's a perspective that's humbling and isolating and profound. Let me conclude with this thought. We live in a moment where we have the technology to explore space. We can send machines beyond our world. We can explore planets and moons and distant regions of the solar system. We can land robots on Mars. We can send spacecraft to the outer reaches of the solar system. But we can't reach the next galaxy. We can't bridge the distance to Andromeda in any reasonable time frame. We can't overcome the scale of the universe. And so we send Voyager. We send it knowing that it will take 2.5 million years to reach its destination. We send it knowing that we probably won't live to see it arrive. We send it knowing that we might never know if it's found. But we send it anyway, because it represents something important. It represents human ambition. It represents our desire to explore, to understand, to reach beyond ourselves. And it represents hope. Hope that somehow, across 2.5 million years and a distance of 2.5 million light-years, our message will be received. Our voice will be heard. Our existence will matter. This is the devastation and the beauty of the Voyager calculation. It's a stark reminder of our limitations. But it's also a testament to human determination and hope. We've sent a machine into the cosmos that will travel for millions of years. We've given it our music, our mathematics, our greetings. We've sent it with no guarantee that it will ever be found, ever be understood, ever matter in any cosmic sense. But we've sent it anyway. And in doing so, we've transcended our human limitations. We've extended our presence beyond the solar system. We've cast our message into the cosmic ocean, trusting that somehow, somewhere, it will be received. This is what scientists are grappling with when they calculate Voyager's journey time. They're grappling with the scale of the universe. They're grappling with human mortality and cosmic timescales. They're grappling with the question of whether our existence matters in a universe so vast and so old. The answer, I think, is yes. Our existence matters. Our message matters. Voyager matters. Not because it will definitely be found. Not because it will definitely reach Andromeda. Not because it will definitely matter in any cosmic sense. But because we sent it. Because we tried. Because we believed that humanity's voice was worth hearing, even if the only audience is the vast emptiness of space. This is the message that Voyager carries into the cosmos. Not just greetings and music and mathematics, but a testament to human hope, human ambition, and human determination. And it will travel for 2.5 million years, carrying that message across impossible distances and incomprehensible timescales, until it reaches Andromeda, until it drifts beyond Andromeda, until it reaches the edge of the universe itself. And in all those millions of years, it will be carrying humanity's attempt to say to the cosmos, we were here, we mattered, our voices had meaning. This is the devastating and beautiful truth that Voyager's calculated journey reveals about our place in the universe. End of narration.